Anyway, if you're looking at the screen now, you should see the table of contents, kind of a summary of what we're going to talk about. First things first, we'll talk about the definitions that we need to kind of get out on the open and make sure we're all talking about the same things. Just kind of define friction and coefficient of friction. Talk a little bit about what the different types of frictions mean, coefficient of friction means, and the different fibers that are involved in the types of synthetic ropes that will be of interest to us today. Some of the system properties involved and how you measure coefficient of friction and why that's important to how those values can be used in both the design of a system or the selection of a rope. Talk a little bit more detail about those fiber comparisons and some of the limiting factors in the typical fibers and high performance fibers used in these types of applications. And then go through a few practical considerations and why this matters in the field in kind of breaking it down into a few different categories. So first things first, friction. A pure definition of the term friction given here is the result of microscopic roughness of the two contact surfaces in question, necessitating higher tangential force to cause relative motion between two objects. So just a quick view of kind of zooming in on what's actually happening at the interface between two objects when they're coming to contact, whether they're in motion or at rest. The next relevant topic is what is coefficient of friction. Obviously, that's the topic of the conversation today. So at the most basic level, trying to understand the two most simplest forms of coefficient of friction. For the purposes of our conversation, we'll be focusing mostly on a quote-unquote dry coefficient of friction, or dry friction, meaning two physical bodies coming into contact with each other. First, the static coefficient of friction. This is the ratio of shear force to normal force between two surfaces at the moment of impending slip. So the important factor there is that last part of the sentence, the moment of impending slip. So this is a representation, a scalar factor that helps represent the grip between two objects that will keep those two objects from moving between each other relative to each other. The sliding coefficient of friction, that's the same ratio of shear force to normal force, but instead this is the scalar that is required to keep those two objects in relative motion. Most of our conversation today will focus on the static coefficient of friction, and that'll make a little bit more sense as we go through it. So, static versus sliding. Why does it matter? As we go through this presentation, you'll see the focus of the conversation is mostly geared around maintaining constant grip between a rope, regardless of the rope's construction or fiber type, maintaining that constant grip between the rope and the actual hardware that it's working on. So this can be something like a load control device, something like a capstan or a towing bit, or something more, apparently more dynamic like driven equipment, independent sheaves, pulleys, or traction systems. All of these things introduce a lot of variables into the equation when you're trying to understand coefficient of friction. So it's kind of an important thing to make sure that all these variables are at least somewhat understood and taken into account. Some of these system type variables may be are listed here. Obviously, this isn't limited to these factors, but these are the primary ones. The contacting surface material, the substrate, in other words, ambient temperatures in the environment around the contact, velocity of the two objects. Again, that's kind of been mentioned already, but obviously that's a factor that will change the coefficient of friction. The forces at play, the substrate geometry. So if you have a round sheave, or even within the realm of round equipment, you have different sizes of sheaves which will change contact pressure, and different surface shapes, and then lubricants involved. These are things like water, oil, or things that are intentionally used to help decrease the coefficient of friction in different environments. And then there's the set of rope design factors that will influence the coefficient of friction between the two structures, the rope and whatever it's coming into contact with. The most basic ones, the most important ones to keep in mind are the coating that's used, the construction of the rope itself, and the fiber coefficient of friction, which will dominate will largely dominate the resulting rope coefficient of friction. So obviously, with a pretty wide list of variables that can impact the coefficient of friction value, it's important that it's understood that this coefficient of friction is a empirically derived characteristic of two physical entities coming into contact with each other. So naturally, with that being the case, the test approach and the test conditions are critical to making sure that the values that you get represent reality, and this is even more important for critical applications where having maximum assurance that no slip will take place is important to the application. So as you see here, this is just a very basic representation of how a coefficient of friction is derived, and as you can see, it has an exponential relationship between the tensions applied on one end of the contact and then the resulting tension on the other end of the contact. And we'll talk a little bit more about that as we go through. So the title of the webinar today is you see mention to the phrase DPX technology. So I think it's important that before we go much further to kind of understand what that is. A lot of our conversation, a lot of the discussion, and a lot of the use of these high-performance synthetic ropes in the industries that we service, the ropes themselves are built from a fiber called HMP. A lot of you may be quite familiar with this. Also, there's common brand names like Dyneema that are used to reference HMP fiber quite often. This acronym stands for high modulus polyethylene, and the reason this is so pervasive in so many industries is because it's a very adaptable fiber type. It has extremely high strength and low weight properties. A low modulus, so low elasticity. It can be used in wire rope replacement quite readily. But it has some drawbacks in terms of its coefficient of friction. It's a relatively slick or slippery fiber, and it doesn't necessarily like relatively high temperature ranges that other synthetic fibers can handle a little bit more easily. So we'll show a little bit more about those numbers in a second. Because of these characteristics, Samson developed a fiber technology called DPX several years ago. And basically what this is it's an HMP yarn or fiber similar to what I just described with Dyneema that incorporates a spun polyester fiber overlay through a patented technology. What this is intended to do is to create a new fiber, a new type of fiber technology, a new yarn that then has a higher coefficient of friction than the typical either uncoated or coated HMPE. Those yarns are then used on the outer surfaces of any given rope construction, and there's several listed at the bottom of this slide, to increase the effective coefficient of friction of the rope itself while minimizing the amount of strength that's sacrificed from providing a surface layer that doesn't contribute to the strength as significantly as HMPE would. So I mentioned there's some limiting factors with the temperature resistance or high temperature resistance of HMP, and I just wanted to kind of put that into some context and quantify it a little bit. You see here, listed here, there's a critical temperature shown under HMP of 150 degrees Fahrenheit, melting point of around 300 degrees Fahrenheit. If you compare those to the other synthetic fibers that are typically used, you see there is a drop-off there. And the reason this is relevant in our discussion today is because sliding or slipping of a rope against the surface, a mechanical surface like a piece of hardware or a stainless steel pulley or anything like that, can create significant amounts of localized heat. And that heat then can create localized damage to the rope itself. And again, for critical applications, that simply would not be acceptable in most cases. So in order to kind of understand how that DPX technology can impact the rope coefficient of friction or the yarn coefficient of friction, I just put a quick summary together here to show kind of a basic guideline or range of coefficient of frictions for the different types of fibers that are used in these types of high-performance applications. So as you see, there's a pretty significant jump in coefficient of friction or effective coefficient of friction in both yarn and rope form when DPX fiber is utilized, getting it more in line with some of the traditional synthetic fibers as well as some of the other high-performance synthetic fibers out there like Aramid and not raising it to the level of steel wire, but putting it much closer so that when you're trying to use these types of ropes in applications, steel wire rope applications or newly designed systems, you have something that has effectively much better performance. So the next thing to probably understand is why does this matter? Just kind of make sure that we take the right things into consideration when either designing a system or trying to identify the appropriate rope product to use in these different types of applications. So what I've done is I've sort of broken it out into 3 basic categories of applications or uses that this issue becomes relevant. The first one is what I've called handling by personnel. So this means that the tension that you see shown, kind of illustrated with the red arrow going out, the working tension in the application is going to be relatively high. You know, different applications have different values, but let's say in the order of 50 to 100 tons or 20 to 30 tons, you're working with a relatively high working tension. And in some applications, it's necessary that personnel is used to handle the lines on the back side, as you see indicated with the yellow arrow there on the left-hand image. So the tension reduction between working load and the back end of the friction device is significant. And in order to reduce that tension dramatically like that, you need to have a relatively high coefficient of friction to avoid that tension transferring all the way through the system. And this will make a little bit more sense as we go through the next couple slides. The next category would be what I've called winch termination, just as a means of simplicity to have this discussion. What I mean by that is there's a more moderate tension reduction that's required simply to avoid having full working tension come onto the connection point to another piece of hardware. So there's just a couple photos here to try to represent some examples where either on a split drum winch where you don't want full working tension going into the storage drum, or you see a pass-through on a winch flange where the connecting rope is a much smaller, lower strength piece of rope that's used to make sure that the rope simply doesn't come unspooled under certain working conditions. Again, those tensions that are expected to be handled in those conditions are much lower, so you still need some tension reduction from working load to the hardware contact, but it's less significant than we talked about with the handling by personnel. The next topic would be back tension control. So this is not necessarily as common, but it's often more critical. You see in the image below, there is a traction winch system, and so the back tension in this system is not necessarily something that needs to be handled by hand or needs to be severely or significantly lower than the working tension. However, it does need to be consistent. So maintaining consistent contact on the driving sheaves or the driven sheaves of a traction system, for example, is critical to maintain a constant tension on the back side of the system for spooling or reeling or any other kind of handling or storing. So in order to try to put all of this into perspective between those 3 different categories, I've tried to put everything into one chart here for review. And what you see on the horizontal axis is the representation of coefficient of friction, and on the vertical axis, the number of wraps required to maintain static conditions. So this is in order to prevent slip, a rough estimate of how many wraps or turns on a piece of hardware, whether that's a sheave, a capstan, or otherwise, may be needed to maintain that pre-slip condition. And what you see on the chart is two vertical buckets of ranges of coefficient of friction that you may see in typical HMPE ropes that are used throughout the industry. And then comparatively, HMPE with our DPX technology on the surface and what those rope coefficient of friction properties typically would be, kind of a re-representation of what we showed in the chart earlier. And so you can see from the chart, if you're looking in at HMPE, the HMPE category, the number of turns for these types of products may be in the range of 15 to 20 turns. That sounds like a pretty significant number. However, if you look at the comparison with the HMPE with our DPX technology, you can see that same condition or same performance requirement can be satisfied with something more along the lines of maybe 8 to 10 turns on the same system. And again, similarly, you can compare how that needs to be handled or considered in the design phase for a back tension control system like we showed on the last slide with a number of, this would represent something like the number of sheaves in the traction system being something on the order of 4 to 6 as opposed to 3 to 4. So that hopefully that kind of helps describe the comparative differences and how it can impact both design and product selection considerations. So I think a lot of the conversation that we've been having so far has been geared around preventing slip. And I mentioned earlier the concern about slip creating high heat generation, localized heat generation at the interface. This is a pretty intuitive topic. I think most people would kind of understand that, but I think it's still worthwhile kind of putting it into mathematical context and making sure it's understood that what's effectively happening here is heat is being generated as energy is being dissipated through that contact, that relative motion between the rope and the hardware. This is in a situation where slip has occurred. So in order to, or by preventing slip, you basically take the relative value of the velocity, which is represented here as v, to 0. And in turn, you're basically eliminating heat generation or significant heat generation because the other values, other variables in this equation are quite constant. The difference in tensions between the working tension and the back tension in most of these systems should be relatively constant as long as slip is avoided. So the next thing to consider then would be hardware design. And in order to do so, I think one of the first things to do is try to make sure we understand all the variables that are at play in impacting the hardware and the forces that could potentially cause damage to these hardware pieces, regardless of what type of hardware we're talking about. But in order to make this conversation a little bit more simple, I focused in on just a simple bollard from that you'd see in several different occasions in the marine industry. You see a very simple schematic on the bottom of this slide with a rope twisted or wrapped around a piece of equipment with the tension going in either direction. You are imparting a force on that, a series of forces on that hardware. There's a lateral force that can kind of be represented by the upper schematic, the simplified schematic, which imparts a bending moment on the what I've called here a beam, which is effectively the bollard. At the same time, that rope wrapping around the bollard, as that coefficient of friction decreases, you get you approach a situation where the tensions on both sides are quite similar. And then as that happens, the circumferential stresses that are induced on the hardware itself become more significant and the bending moment becomes less significant. And in doing so, you approach a situation or you risk a situation where the hardware design may not be sufficient to handle those hoop stresses, and you risk potential collapse or compression of the actual walls of the hardware structure. As a very vivid example of this, I'm sure many of you in the marine industries may have seen something similar in the past. This is a fairly common scenario that we see with the relatively high strength of these HMP rope products. One of the downsides is as that circumferential hoop stress gets imparted on these pieces of hardware, the lower the coefficient of friction of that rope is, the higher the hoop stress is going to be. So if these pieces of hardware have been designed to resist beam bending, so in order to resist the bending of the whole bollard structure, for example, they may or may not have taken into account wall thickness in these designs sufficient enough to avoid that hoop stress causing potential collapse. So what I've shown here is a very, very primitive schematic of incoming and outgoing tensions on a wrapped bollard, for example. And as you saw on the previous slide, this bollard has seen sufficient enough hoop stress or compression and stress to cause a collapse, which is obviously critical and a major impact to safety on board. In order to describe this a little bit better, this schematic is just intended to show that as T1 is a relatively constant value, regardless. So in most occasions, there'll be some force being applied to the system that's trying to be maintained, hence the use of the rope in the first place. As that value is relatively constant, there's a couple conditions that can apply here. If you're using a relatively high coefficient of friction rope, so as that coefficient of friction increases, your level of grip on those first layers is relatively high then. And in turn, the T2 value that you see on board the vessel is as low as it can be. However, as that coefficient of friction approaches lower values, and let's say for the sake of argument approaches 0, you get in a situation where T1 then approaches T2, and the stresses at work on the hardware are approaching purely circumferential hoop stress. And in this case, the design of the hardware is critical to assuring that it can withstand that hoop stress. And alternatively, the rope product selection is important to avoid a situation where that compression is so high due to the fact that the tension on the working side of the system is transferring all the way through to the back tension side. The other type of system considerations is a bit more straightforward, but also very important. When you're dealing with these ropes driving relatively large equipment, for example, something you see here, relatively large and in turn very heavy pieces of mechanical equipment, it's important to assure that both the coefficient of friction is sufficient to avoid relative slipping, but also that the system is designed to allow for freewheeling turning based on the planned coefficient of friction and friction force that's going to be able to be applied by the product itself. So in conclusion, there's several components to this topic that should all be taken into account. The design considerations, the system versus the rope. Both approaches need to be taken into account. The appropriate rope coefficient of friction will, in fact, impact performance, as most of you know. But at the same time, on the design side of the hardware or the system that's being used, careful consideration can be used to help avoid any potential conflict with whichever rope is being used in your given instance. The prevention of slipping is critical to avoiding rope damage, so both on the product selection side, making sure that you're picking a product that won't slip, but on the usage side, making sure that you're maintaining proper number of wraps to avoid that slipping given whatever hardware and rope product you're actually using. And critical to both safety and total cost of ownership, it's important to avoid hardware damage through product selection and proper design considerations, as we've been talking about throughout this presentation. Samson can help with those types of considerations for more critical applications where specific physical parameters need to be checked to assure that the most accurate system is being designed. And obviously the DPX technology that we've been talking about allows for this added control in the use with HMP ropes with minimal sacrifice to other performance properties like tensile strength, abrasion resistance, and others. That is it.
Okay, thanks, Chris. That was great. If we do have time to have a short question and answer period, if anybody does have any questions, you can enter them in the lower right. There's an option to type in questions, and then Chris can answer them here for you. We will also be recording. We've been recording the webinar, so we'll be posting that to our website within the next day or two if you want to take a look at it again or share it with colleagues. So we'll go ahead and just pause for just a moment here and give you a chance to formulate a question and send it in. Okay, it looks like we do have a couple of questions. Does DPX have any negative effects on rope performance?
I kind of alluded to it a little bit at the end there, but effectively the short answer, the easy answer is no. Everything with rope design, there is a trade-off. So the addition of the DPX fiber does, in fact, create a relatively small drop-off in new rope tensile strength. This happens because as you introduce the DPX fiber, you're basically eliminating a small percentage of actual HMP fiber, which is the load-carrying fiber in the system. So when you're talking about diameter to diameter comparison, yes, you will have a very small drop off in strength. However, it's effectively as small as you can get while adding the grip characteristics that you see that we talked about today. However, the abrasion resistance is typically quite good in our DPX-based products, and also all the other typical characteristics you get with HMP fiber: high cut resistance, very good tensile fatigue, very low weight to strength ratios. All of those things still hold true as they would with 100% HMP rope.
Okay, we do have another question. How does the rope construction itself contribute to coefficient of friction? The difference between 3, 8, and 12 strand constructions.
Yeah, that's a very good question. I mentioned towards the beginning of the presentation that the fiber properties typically are the most predominant factor that drive rope coefficient of friction. However, you're onto a good point there that the rope construction does indeed have a impact on effective coefficient of friction. The difficulty in answering that question with one straightforward sentence is that the different rope constructions will interact differently with different hardware configurations. So to put it a little bit more simply, for example, a 12-strand rope is a relatively round, hollow structure that can form to different shapes and hardware conditions. Whereas an 8-strand structure is a more solid braid that has, for lack of a better term, has knobs that are natural to the actual braid, and therefore, with the right type of equipment, could in fact have an even better or higher coefficient of friction and better grip. But with the wrong type of sheave or smooth, round sheave, for example, it may not have nearly as good coefficient of friction or high coefficient of friction as something like a 12-strand product. So to summarize that, I would say that the best thing to do in critical applications is to consult with the rope manufacturer and make sure that you understand how the product selection can impact it, and if it is ultra critical, even go to the lengths of testing or testing a more representative system to assure you understand the actual coefficient of friction.
Okay, good. It looks like that was our last question, so we can wrap this up. Well, thanks again to everyone who attended, and also thank you, Chris.
Thank you.